when we start looking, the first part is when we start looking at rectifiers, we only look at the discrete components, and then at the end of the webinar we'll be looking at the actual application of these in a circuit. So let's have a look here. We see that the rectifier definition, well, it's a diode really. There's nothing different from a rectifier diode and a normal diode, in the sense that it has a forward bias and it has a reverse bias. So in forward bias, current can flow, and in reverse bias it doesn't flow. So this is the same for all diodes. The difference with the rectifier diode is that it has a very high current rating and also a high reverse voltage blocking rating. So the current flow is the main thing that distinguishes these types of diodes from other types. Okay, so as I said, they can be discrete, or they can also be as part of ICs for smaller applications. For the very large applications, they are part of what we call them modules. We don't call them integrated circuits. They are modules, typically for very large three-phase applications. We have 6 diodes packed into a very large module, with designed actually to be mounted to a heat sink and with thermal paste in between. So these are the different packages that you find them in. So this one on the left here, this is just a generic diode with a slightly higher power rating. It's the same as the one in the center diagram, and the one on the right is a surface mount device, also a rectifier diode. The next type of diode we're looking at is the Zener. Zener is a very interesting diode. It's actually operationally the same as a normal diode in forward bias. Now in reverse bias there's a slight difference, and that is that it doesn't, when it goes into breakdown mode, it doesn't actually self-destruct. It can actually happily operate in reverse bias mode past the breakdown point, and then past the breakdown point it will basically keep the voltage constant across its terminals with a wildly varying current flowing through it. So this is a typical circuit for where we use one of these interesting diodes as a voltage regulator. So we have a voltage source over there, then a series resistance, and the diode in parallel with that combination. So this is a better circuit on this page. It's just a better definition of all the symbols. Once again, we've got an input voltage, and over there we've got the output voltage. So the Kirchhoff voltage law is very easy for this circuit. It's simply that the output voltage is equal to the input voltage minus the voltage drop across the resistor, which is IR. So we can write this equation, V out equals V in minus IR. Okay, and then we know already that the Zener diode clamps voltages. And we also know that it works in reverse bias. In forward bias, it will just be simply a normal diode. So what happens in this circuit is very interesting. We have basically 2 operations that you can combine. The first one is the V in minus IR, which we can draw as this dotted line over there, or the dashed line. The other one is a constant voltage division for varying currents until you have the breakdown. Well, actually, where the IR voltage drop is large enough to take over. So in other words, when you just look at the 2 intersects of the 2 drops, then you can combine these linearly to get the voltage transfer of this circuit. So it's a very good regulator for the majority of the operational mode. It uses it carefully, and it operates over here then it's a very good voltage regulator. If the current becomes too large, the voltage will start falling backward, will start decreasing. Right, we can also use Zener diodes for other applications. We can clip voltages, so this is just a very typical generic application in this circuit. So we've got once again an input voltage, a series resistor, and then two Zeners. Or one Zener, and then the difference with the previous circuit is that we actually have another Zener connected in the opposite direction. In other words, when one is reverse biased, the other one is forward biased. So then what happens if you have a sinusoidal voltage applied to this circuit, then that let's say in the positive half cycle, Zener 1 will be forward biased, Zener 2 will be reverse biased, so Zener 2 will be blocking the voltage or clipping it. As you can see over there, that's the Zener voltage that it would be clipped at. Right, and then the opposite is also true for the voltage in the negative half cycle. So then the forward and reverse bias are just swapped. Okay, if we connect the circuit in a different way, we place the Zener diode in series with the voltage source, and then the load resistor in parallel with the combination of a voltage source and Zener. We get a different type of circuit behavior. This is what we call a voltage shifter. So this is a function of time. This is a voltage. And the solid graph over here is the output voltage. Now what happens is, as function of time, we have this linearly increasing voltage Vin. Now what actually then happens is, because of the fact that there's a clamping action going on in the Zener, it will hold the voltage for a while, and then after this point, it will just basically shift the voltage to the right. So it gives you a shift in time for a waveform. So this is a very simple waveform, which is linear, but you can use this for other voltages as well, for other voltage waveforms as well.